Okay, this is the second video in our projectile motion on our projectile motion topic. This is slightly different from the first one. So here what we are seeing is that an object is thrown from a cliff of height 120 meters. So this is my cliff. This is my cliff, and the height of the cliff is 120 meter, and this object is thrown at an angle 90 degrees below horizon. So this is how the object is being thrown, and it hits the ground here. The ground is not horizontal, so let me draw it again. And my initial velocity is this, which is 42 meter per second, and that angle is 90 degrees. And this is part A of the question is asking us to find this range here, R. We need to find the R, and second part is finding the velocity at this point B. Let's call it point B. With what the velocity with which it would hit the ground. So we'll start with part A. So again, we already know that in projectile motion, the time of flight is determined by considering the vertical motion. So let us consider the vertical motion here. I'll write that heading. I could write considering vertical motion, but even if you write this vertical motion, it is enough. So initial vertical velocity I'm talking about here is 42 sine 19, and that is equals to 13.674 meter per second. Now this velocity is downward, this initial vertical velocity, because my velocity is this. So you will have one horizontal velocity going like that, another vertical velocity going like this. So this vertical velocity is downward, which means that I'm taking downward direction as a positive direction. And because downward direction is positive direction, my acceleration, which is due to gravity and which is 9.8 meter per second squared downward, vertically downward, so I will have to give that also as a positive value. So this is 9.8 meter per second square. S, how much is the vertical displacement between the launch and the landing? So it is launched from here and lands at point B. So from point A to point B, my displacement is 120 meters downward. I mean, you started from here and landed here vertically. So again, it's vertically downward, so I will have to take that as positive as well. And the equation that I'm going to use is S equals to ut plus half at square. All right, so let's put the values there. And S equals to 120 is equals to 13.674 t plus half times 9.8 t square. I can write it like this: 13.674 t plus 4.9 t square. And I can write in standard form. Standard form is that everything should be standard quadratic equation has all the quantities on the left side. So 4.9 t square plus 13.674 t minus 120 equals to 0. Now this is a quadratic equation, and we could use the quadratic formula as well to solve this, which, because the all the numbers have got decimal points and all these things, would be a tricky task. So what we do is, we put this in a graphing calculator and plot a graph of this expression, and then we find the coordinates of the point where the graph crosses the x-axis. So when we do that, we find that there are two solutions. One is t is equals to minus 6.537 second, and other one is t is equals to 3.745 seconds. So time can never be negative. So our valid solution is t is equal to 3.745 seconds. This negative time here, if you look at it mathematically, what it is saying is that let me draw it here. I'll erase that later. That your object is starting from here, landing here, and this is your time taken. But if we go back in time, you will find that at minus 6.537 it will be back on the ground. So displacement will again be 120 meters from here, but 120 meter downward. So that basically is telling you the time when it hits the ground, if we theoretically extrapolate it back in time. Okay, so we got this time of flight here. Now finding the horizontal distance is straightforward. Horizontal range is, all this can be found by multiplying this time of flight with a horizontal velocity. Now horizontal velocity, just to repeat that, it is constant. It's a constant velocity. Problem here now, because there's no acceleration in horizontal direction. Whenever something is moving freely in Earth's gravitational field, the acceleration is always 9.8 meter per second vertically downward. So I can find my horizontal range by taking initial velocity, or the same velocity, constant velocity is 42 cos 19 degrees, which basically is 39.71 meter per second. So object is traveling with this velocity all the time. It is in air, which is 3.745 seconds. So range is equals to r is equals to u times t, which is 39.71 times 3.745 second, and that gives us 148.72 meters. That is my part A of the question. Now when we look at part B, here to find with what velocity the object would hit the ground. So if we look at our result velocity at the launch point, we saw that there are two components. You got one horizontal component and one vertical component. So this initial velocity has been resolved into two components here, and I can independently consider them because any motion in one direction is not affecting the motion in other direction. Okay, other way to look at it is that I have broken this velocity into two parts, and if I put them back together, I get my velocity back, as we've seen in the previous video. Now if we look at the launch point, at the landing point, we see that this landing point also we can consider, we can take into account, or we can calculate two components of the velocity. So at the landing point, you will have a horizontal component and you will have a vertical component. Now horizontal component in the horizontal direction is constant because there is no acceleration in the horizontal direction. All the acceleration is in the vertical direction. So our problem basically is of finding the vertical component at the point of landing. Now that's easily done. We just consider the vertical motion and then we find the final velocity at this point. So let's first list the quantities. I'll again state that I am considering the vertical motion. So at the point B, my vertical motion initial velocity at A at the start of the launch is 42 sine 19. We already found here when I consider the vertical motion in part A. This is 13.674 meter per second, and because this is vertically downward and my vertical downward direction is positive, acceleration is 9.8 meter per second square. And this time now I know the time of flight. I know that from when it traveled from A to B, it took 3.745 seconds. Yeah, so all the time the object is in flight, it is getting vertically accelerated downward by 9.8 meter per second square. So all I need to do is now find the time after 3.745 seconds. So I need to find the velocity at the launch point, which is my V, and that's what I need to find. I will use the equation V is equals to U plus AT, and again this is all vertical I'm talking about. Everything is vertical. So V at 3.745 second is 13.6745 plus 9.8 times 3.745, and that gives you my vertical velocity of 50.375 meter per second. So just to repeat that, at the landing point B here, this is my vertical velocity. Okay, how much is my horizontal velocity? Let me again, just to be clear here, let me write here, this is vertical component at the landing point. Now what's the horizontal? I can consider horizontal motion. What's the horizontal velocity at the landing point? Okay, but first here, this is V here, but to be more clear, let me write that as VV, which basically means it's the vertical velocity. So what is my horizontal velocity, final horizontal velocity? I will call that as VH, and because there is no acceleration, it's the same velocity and it's not changing. So we found the velocity in part A. The horizontal velocity is, I found it at 39.71 meters per second here. So this is 39.71 meter per second. Now to find the total velocity at point B, all I need to do is I need to add these two components, this horizontal and vertical, and adding these is straightforward. So we draw them in a chain. So I will draw the horizontal first. That's my horizontal. The length is 39.71, and the vertical is downward like this. This is 50.375, and my final velocity is that. So, and this velocity I need to find. This angle is 90 degrees. Using Pythagoras theorem, I can straight away see that V is equals to 39.71 square plus 50.375 square, and that gives me 64.14 meter per second. But that's not the end of it. I need to, because we are finding velocity is a vector, which means we also need to find its direction. So I can find that angle. In this angle, I can calculate tan theta, which is 50.375 over 39.71. That gives you theta is equals to tan inverse 50.375 oblique 39.71, and that gives me theta is equals to 51.75 degrees. Now merely finding the angle is not enough. We need to put in proper frame with the proper reference. So I will say V is equals to 64.14 meter per second, 51.75 degrees below horizon. So I can see here, because this is my horizon here and this is my velocity, so it is below horizon here.